Okay, this video is for AP Calculus BC. This topic is specific to the BC part of the course. We're going to talk about two other uses of integration to do applications. One is Arclength and one are surface area of surfaces of revolution. These are actually a little easier than the previous sections. I would say most students find these to be a little bit easier. First, let's talk about something called arc length. We've been using integrals so far to add up elements of area and volume, but we can also use an integral to sum up small linear segments to find the length along a function curve. So maybe you want to know, like maybe this represents like the flight of a bird, and you want to know what's the distance that the bird has flown. So the way we can do this, let's derive this this formula. The way we can do this is we can divide that arc length up into a little series of finite length line segments, because it's easy to find an equation of a line segment. I'm just going to use what's called the distance formula. Let's just take an example over here. If I have 2 points on the xy plane, and let's say that this point is x1, y1, and this point here is, well, let's just use this generic one up here, x2, y2, then what would this distance d be? Well, that distance would be this. If I made a right triangle out of that, this is the change in x's, which is x2 minus x1, and this leg over here is the change in y's. And the Pythagorean just says that that the distance squared here, the hypotenuse squared, would be the sum of the other two legs squared. And if I just take the square root of that, I get the distance. So this is just the Pythagorean theorem, but it can be rearranged to form what we call the distance formula. And that means that the distance on a little segment here would be, if we were to start, say, at a point that's on this curve P1, and then you go a little bit further in here, and you add one to that, and you continue to add one to that. Each 2 points that are next to each other, we can find the line segment by just taking the difference between the current one and the current x and the x for the point before that. Take that difference squared, the difference in the y squared. I'm going to write this difference here as delta x. So just imagine that this little difference here is delta x, and this difference here is delta y. That distance is delta x squared, the square root of delta x squared plus delta y squared. And then if I sum them up for each of these, that gives me an approximation to that line segment. Right? But what I would really like to do is to bring these points very close together, so we're almost perfectly tracing this out, and then define the actual length to be the limit of, as n approaches an infinite number of those little points. Right? So if we've got that, this is the structure that will give me this, then, well, I know one other thing too. I know that because of the mean value theorem, if I take any 2 points here, right, because this function is continuous, defined over the interval, and differentiable, that means that the derivative exists. And that means that there's got to be some x in each of these intervals where the rate of change, the average rate of change, delta y over delta x, equals the instantaneous rate of change at that x. So that can be used to solve for delta x. If you just multiply both sides by, or for delta y, if you multiply both sides by delta x, delta y is equal to delta x times the derivative. And that means that this delta x can be replaced with the derivative of f prime times delta x. And then what you can do is take this delta x squared and factor it out of both terms here. And then since that's still under a square root, the square root and the square root cancel and give you delta x. And that means that this is equivalent algebraically to the square root of 1 plus the derivative squared, and then times delta x. So now if we do a smooth sum, this turns into the definite integral from a to b of this integrand, and this delta x becomes infinitely small dx. This is called the arc length formula. So let me write it again. The length along this path, if I have a starting x and an ending x, is going to be an integral from that starting x to the ending x of the square root of 1 plus the derivative of x, but squared, and then integrated along all these x's. Right, so there's the derivation. You're not required to be able to reproduce the derivation, but you are required to memorize the result. So let's actually work a problem with that. This says graph this function and visually estimate its length and then find its exact length. Okay, so they're asking me to graph this function. Let's do that with a calculator. Let's clear out what we have here currently. Here. And we'll go ahead and enter this. This is x cubed divided by 6 plus, got to be careful here, 1 divided by parentheses 2x, because the 2 and the x will both be in the denominator. Okay, now if I graph that from, let's see, we're graphing from, let's graph from 0 to 1 actually. I'm going to graph from 0 to 1 in the x. Actually, let's make this the same scale. So if I go from -2 to 2, -2 to 2, that way I can estimate better. Okay, so here's the function curve. And we're estimating, if I go from 1/2 x to 1, I want to estimate this length right here. So I'm thinking if this is 1, this length right here seems to be a little less than 1, like maybe 0.8 or something like that, 0.7 or 0.8. Let me make a sketch of what we're seeing here. Okay, we're seeing a graph that in this region looks like this. And from 1/2 to 1, this part of it, if I were to kind of highlight it, this length here is maybe on the order of 0.7 to 0.8, somewhere in there. Okay, so now we have a mechanism to find exactly what that length is. We're just going to use the Arclength formula. So first of all, I'm going to need the derivative. So what is the derivative here? This, let me rewrite this. Y is 1/6 x cubed, and then this is a 1/2. This x is in the bottom, so that is x to the -1. That will allow me to take the derivative. So the derivative here is 3/6, which is 1/2 x squared, and then minus 1/2 x to the -2, which means that the length, the path length, is an integral from 1/2 to 1, because they told me to integrate over that area, the square root of 1 plus the derivative of the function, 1/2 x squared minus 1/2 x to the -2 squared, and then dx. And if you plug that in, you end up getting that it is 0.646. So we were a little high on the estimate. It's actually just under 0.7. All right, that's all there is to it. There's a formula. There's a lot less going on geometrically. You just have to have the function curve and take the derivative to plug that in, and then have the boundaries, which are often given in the problem. Okay, go ahead and pause the video and try this one on your own. Find the length of the curve. Not going to bother to sketch. We just know that this is going to be an integral from a to b of 1 plus the derivative of the function squared dx. That's the pattern. So I need the derivative of this. Let's compute that over here. Y is 1/4 x to the 4th plus 1/8, and that's x to the -2. That's a 2. Y prime would be 4 times that, so 1 times x cubed, minus 2 times 1/8 would be -1/4 x to the -3. So this is going to be an integral from 1 to 3 for x, square root of 1 plus that derivative of x cubed, minus 1/4 x to the -3 squared, that's all in the radical, dx. And if you do Math 9, that turns out to be 20.111. Okay, so that is Arclength. Not too bad. Let's do one more variation on this before we move on to surface area. So let R be the region enclosed by these two graphs. What's the length of the boundary region of R? I think we should use a calculator to graph to see what's going on here. So if I go and graph natural log of x squared plus 1, and then cosine of x. Let's just graph origin plus minus 10 at first. There's the natural log curve, and then the cosine curve. It looks like everything's happening right around here, region enclosed. So let's zoom in to about plus or minus 2 in x and y. And here's the log curve, and here is the cosine function. So there's sort of a eye-shaped region enclosed there. What is the length of the boundary? Okay, I think I'm going to graph this. Let's actually know where the intersections are. I don't think these are integers. So if I were to go second trace integer, and say, let's go to this one over here. First curve, second curve, guess. Sure enough, that's at x is 0.9159 and y is 0.6091. All right, so I'm going to sketch this thing. What we just found in the calculator. Okay, we found that it looks something like this. There was sort of a log curve that, exaggerating with it, looked like that, and then there was a cosine curve that looked like this. And so it was this region in here. That's the region enclosed. We want the length of the boundary. Okay, so first of all, the boundary consists of two sort of fences. There's that fence, and then there's this fence, right? So let's work on each of those, okay? The arc length for this red boundary is going to be using the cosine curve. That's this curve. And so that length is going to be an integral from, let's see, the low end here. I've written down what these were. This point over here, fifth intersection, is negative 0.91586, comma 0.60911, and this is symmetrically positive 0.91586 to 0.60911. So that means we're going to start at this x and end at this x. Negative 0.91586 to positive 0.91586. And then we will take the square root of 1 minus and then the derivative. So the derivative here would be negative sine of x. So I'll plug in negative sine of x, and then that is squared dx. That would give me the area there. And then for the purple area, it's the same x boundaries. We'll add on to that because this is additional boundary. From negative 0.91586 to positive 0.91586. Square root of 1 plus, but now I need the derivative of this. So the y prime here is derivative of log is 1 over the input times the derivative of the input with the chain rule. So we're going to have 2x over x squared plus 1 in there for that derivative that's being squared. And if you were to evaluate this out, this ends up being 2.030386 or so, and this one ends up being 2.25176 or so. So when you add them together, you end up getting 4.282 when you round finally to 3 decimal places. All right, I think I should mention one other thing before we go on to the surface area revolution, the other topic, and that is, why am I always choosing dx? Well, you can actually choose either one. Let's take this red curve for a second. When I'm evaluating this, right, you can choose to integrate this way, which is sort of like saying, okay, I'm going to start at this a and this b, and then that means if you're integrating that way, that means it's like you're doing sort of disk method with a little shape here, right? The dx is still a little change down here, It's just that you're not doing any rotating or making areas or volumes out of it. You're just taking literally the area. The way you can kind of think of it is this way. The domain is the x in this case. And then when you multiply by, so this dx is a little distance here in the domain. When you multiply by this factor here, what you're doing is you're scaling it up to be the length along the path, which might not be the same length as this. So like if you have like a 0.0001 length here, this might be 0.0003 because of the shape of the curve. So this little multiplier here scales this up to be along the path length, and then you're integrating it along that domain. But it is certainly true that you could choose to use the other axis as the domain and integrate that. You could integrate from 0 to y. The only thing is, you would then have to have everything written in terms of y, which means you would have to resolve these for x. This one's not too bad, but it involves arc cosine. This one is a little trickier. So for example, on this one, if you had y equals natural log of x squared plus 1, you could take e to both sides to get that e to the y is x squared plus 1. Then that means x squared would be e to the y minus 1. So x would be plus or minus the square root of e to the y minus 1. Right? So it's more complicated. So if this is a y, we tend to just use the other variable as the integration variable. And if this were solved for x, we would switch to the other direction. But technically, you can do it either way. There's no rules like perpendicular or parashell or anything like that. Okay, there's one other topic to talk about here, and that is called the surface area of a surface of revolution. So if we take a path length, like we just defined this red path length, if you do decide to rotate that path length around an axis, it will form a skin, which is called the surface area of the surface of revolution. Right? So it's not the space inside that, it's literally the area, the two-dimensional area on the skin. Right? So how can we make a formula or an integral that will find that? So what we do is we take the dx, which is in our domain. When we multiply by the square root of 1 minus f prime, that scales it up to be a little piece, an element on the path length, right? And then we're going to rotate that into a little strip of area, right? And the way we do that is we just take that little width here and multiply by the length around the strip, which, because it's a circle, is the circumference 2 pi r. So we just have to take the arc length area, the path length area that we had before of the arc length, which was this, and we have to put an extra multiply by 2 pi r in the integrand to take that and effectively spin it around into a circumference of those path lengths. And then we sum that up, and that gives us a surface area, which would be a two-dimensional result. Okay, so let's do an example of that to show what it looks like. Here, I've got 3 examples here in the lesson to finish it up. Find the area of the surface obtained by rotating this curve around the x-axis. Okay, so now this we do have a rule. We have to treat it as if we're doing disk for the shadow. So we're going to kind of set it up like disk method for the purposes of establishing what we're doing here with the calculation. So let's sketch first. Y equals x cubed looks like this, but it kind of looks like this in the first quadrant. We're going from 0 to 2, and that means that 2 cubed would be up to 8. But we're talking about not an area, we're talking about the curve itself. So I'm taking this curve right here, and we're rotating that around the x-axis. Right, so here's the x-axis, we're rotating it around there, that makes that is going to produce a shape. Right? But I'm not talking about the volume inside there. I'm literally talking about the area on the skin, the surface of this, like the piece of paper that would be around it. Right, so the way we'll do that is we're just going to take the formula. So the formula says that that surface area, so it's a surface area, is going to be an integral from a to b of 2 pi r, and then times the arc length formula, 1 plus the derivative of f of x squared dx. Okay, since this is expressed in terms of y, and more importantly, because this is rotating about the x-axis, that means we are going to have to imagine that we are putting sort of like we're going to do a rectangle, perpendicular to the axis of rotation, which does make this dx type. The dx is down here. By multiplying by this, we get a path length on that. By multiplying by this, we spin that around to make the circumference strip, and then we sum them up. So the final integral here is integral from 0 to 2, because they gave that in the problem. 2 pi, this radius is the radius out to that element. And so this is a y established by that curve, so it would be x cubed. So this is x cubed, and then the square root of 1 plus the derivative of this same curve, which would be 3x squared, but the derivative squared dx. So this is the appropriate integral to set up. And this would be, by math 9, equal to 203.044, and it would be square units if we had units, because it's an area. All right. So arc length, you can actually do dx or dy, but if the function is expressed using y, we choose dx. If the function is expressed using x, we choose dy, so that we have the right letters in the derivative. For the surface area revolution, it depends upon the direction that you would have to be perpendicular to the axis. So you do have to think of it kind of like a disk problem. You would still put a rectangle on here to identify that that's perpendicular to the axis, so that's a dx type. If you had something that was rotating vertically around the vertical axis, then that means that this would be a dy type, so you'd have a dy here. So it's dictated by sort of like the rules we use for disk building. Okay, 2 more quick examples. The given curve is rotated around the y-axis. Find the area of the resulting surface. All right, so this is solved in terms of x. I don't really even need to sketch it in this case, and we will typically not require a sketch on our tests on this. But I know that surface area has this formula in integral a 2 pi r square root of 1 plus a derivative. Now, here's the thing. Since this is solved for x, that means this is going to be a function of y, so that this can be dy out here. Right? And the radius is just from the axis of rotation out to that location. So this is just going to be from 0 to 1. 2 pi, this is just the, one sec here. This r is just going to be the equation of the curve, 2y minus y squared, square root of 1 plus the derivative of that. Now, I think we'll have to be a little more careful here. What is that derivative? This is, x is 2y minus y squared to the 1/2 power for the square root, which makes that derivative 1/2 2y minus y squared to the negative 1/2 times the derivative of the inside, which is 2 minus 2y. So that means that for this, we're going to plug in, I'm not going to try to simplify, I'm just going to plug it in, 1/2 2y minus y squared to the negative 1/2, 2 minus 2y, and then that is squared, dy. Now, unfortunately, this would be quite tricky to plug in a calculator. This video is already a little long, I'm not going to do that, but if you do plug all that in, you get 7.193. Okay, and then one more kind of application problem. A manufacturer of corrugated metal roofing wants to produce panels that are 28 inches wide. So they have to end up being 28 inches wide and 2 inches thick, and they have a wave to them. The profile is supposed to take on the form of a sine wave. Verify that the sine curve would have the equation y is sine of pi x over 7, and then find the width of the flat material that's needed to bend up into that shape. So this length here, this width, is actually the arc length along the surface. So if we could come up with a function here, and that means we could put like a coordinate system on here and say, this is x, this is y. This is going to be from x equals 0 to x equals 28. But we want the arc length to be the longer thing so that we get this function, this sine function. And they're saying that this is sine of pi x over 7. So we can verify that with a calculator. If we grab a calculator and plug in, here it is, and plug in sine of pi x divided by 7 and graph that from, let's graph that from 0 to 28, because we're thinking we're going to go from 0 to 28, actually 0 to max of 28, and then let's go with plus or minus 4 or something, just to see. Okay, so if this is right, wait a second, pi x divided by 7, that looks like it, well, it definitely traces this out, but it has more waves than that. Is that okay? Did I put this in correctly? Nope. It needs to divide by 7, not 4. Let's try that again. Okay, that looks right, where it's got one complete cycle and then another part of the cycle there. Yep, that matches. Okay, so this matches this. There's a 7 down there. All right, so then we're just going to find the arc length along that path, right? This is an arc length problem. So let's grab a pen. This arc length here, the length is going to be, which is the width of their panel, is going to be the integral from x is 0 to x is 28 of, the formula is the square root of 1 plus the derivative of this function, which would be cosine of pi over 7 times x, but then times the derivative of inside, which would be pi over 7, and then squared dx. And if you plug this into a calculator, you end up getting 29.361, and the inches here would be, the units here would be inches because this is a length. So sure enough, you have to have something 29.361 inches long so that when you bend it up, you get this perfect sine wave that has that many periods with a height of 2 inches. Okay, so kind of an interesting real-world application. And that's the last example for this. There's one more video in this sequence, or one more topic to cover on these geometric and related applications of integrals.